Hello. So I wanted to build a machine learning model that plays a game. So the game that I want it to play is called Cart Pole. Is you basically have a block with a pole on top. The idea of the game is you have to keep the pole upright. If the pole falls 15, 12 degrees to the left or to the right, then the game ends. That's essentially the idea. And so what I'm going to use is OpenAI's Gym library to hold the game or open the game in Python. And then I'm going to use a baseline's learning models to or learning frameworks to build a learning model on top of that to play the game. Yeah, so I'm just going to jump straight into it. So just before we start, we need to install these dependencies. So before we go into that one, install gym. So that's the actual library that hold the game. Stable baselines 3 that will actually hold the machine learning framework. And we want to install PyTorch. Now PyTorch is this. You want to install the stable version. I've got a Windows machine. I'm using pip because I've got Python. I'm using Python. Python, obviously. And because I have a Quadro graphics card that enables CUDA, I can install CUDA, this CUDA version here. Really, you want to go to NVIDIA's website to check whether you can use CUDA or not. CUDA really speeds up your machine learning models and the way it learns stuff. Now, if you don't want to use CUDA, you can just click CPU and then install it that way. But since I have CUDA installed, I currently have CUDA 11.2 installed on my machine. If you want to learn how to use CUDA, there's a video on my YouTube channel about how to install CUDA. So yeah, go from there. Once you have that installed, everything should be good, no errors, and you want to install it here. So you want to do pip install gym like that, and you see it installed. I've already have installed, so nothing happened, and the rest you just install here in your terminal shell within PyCharm because your virtual environment is preset here already as well. So yes, so now that we want to import, so we just want to get started and actually build some stuff. So we want to import the gym library uh, where we're going to hold the game, and then we want to build an environment that is gym. Nope, gym.make, and then we want to use a keyword here for what the game is actually called, and we're going to use cartpole version 0. So what we also want to do is say state equals environment dot reset. So that basically sets the environment to start to play. So it basically starts the whole game from the beginning because when you run this, it might just start then. So you want to have at least some way you know where things can start running from. So now we want to say from or for underscore in range, let's say 10,000, let's say 100,000. And then we want to say environment dot render our scene, and then we want to say print dot not dot quote stop. So what this does is builds the game, start the game, go through each scene when you render each frame of the game. So if we run this as is, then you see we stopped here, and you can see. Hang on, let me see if it's up. Yeah, so you can see the frame frozen on screen of what the pole game should look like. So cool, we got that right. All right, so now if we go into our console, and because the way we're running this and we put it in debug mode, we can kind of execute lines of code within our console. Now, if we look at our environment, it's an object, great. Now, if we look at action space, you can see we say when we print out something, it says discrete to. It means these are two options that are available to us. So think of this as the two inputs that the user can apply to interact with the game. So as a user, I can move the block left or right, and that's denoted through 1 or a 0 within this kind of space, this game space here. So when we run our machine learning model, we're going to be passing in these um, values into the game so it can play it. Now, for now, we're just going to make this completely random. So if we say something like action equals env dot action space, Now it's a bit annoying that autocorrect's not working here. Usually it does, but sometimes PyCharm can have a hissy fit, so you never really know. So yeah, this action here just gives us one of the actions randomly. So think of it like this: env dot action space dot sample. It just gives us a random number back. So from what we can provide as an input. So assuming we can pass in as input 0 or 1, it randomly chooses a 0 or 1. So this is a good way to kind of benchmark our game to see everything's functioning and to see if our actual algorithm improves any better than just pure randomness. So now that we're getting action here, if we then make a tuple here saying state reward uh was it info? Done info equals environment step, and then we're passing in the action into that. So basically we're saying render the scene, generate a number between the actions that we have, so that's one, either generate a 0 or a 1, pass that into our environment as a step, so as an input into the game, and then return us back a state, a reward, whether the game has finished, and information. And then we want to say if we are done, then, so as in if the game's finished, then I want the state to equal reset state env dot reset. Yeah, so basically we're in a really long loop here, and we should loop over the whole thing until we finish, which should be, yeah, env dot close. Okay, so let's run this again. Oh, indentation error, my bad. So yeah, let's run this again, and now what should happen is, so in the actual code, it's so that if the pole manages to move from the angle 0 to either negative, yeah, so assuming your degree is 0, 12 degrees to the left, 12 degrees to the right, then the game is assumed to be finished. So that's when the done action here becomes true. So if we click that, we look at done, done is true, we reset our environment, and then run again. Yeah. Okay, cool. So we know the game's running. Everything seems fine. We've got no errors. We've got no red stuff coming up in our console. Cool. Now, let's just comment this out for the time being because we know everything works. Code, comment line section. You can use control forward slash, but for some reason my computer doesn't seem to understand that right now. So, yeah, so once we have that, we want to do some more imports. So let's try some other stuff. So we want to import now stable baselines dot comma common dot vec environment import dummy vec envir, or environments are short for that. So what this does is it creates a vec, it creates a wrapper around the information we're going to pass to the machine learning framework. Bit confusing right now, but bear with me. Hopefully it'll make sense to you. So what we want to do is we want to create a dummy vector. So we want to do this. So we're basically saying our dummy vec environment lambda colon environment. So for those of you who don't know what lambda does, it's kind of shorthand for a function. So let's say, as an example, let's open a Python console up. So let's say we wanted def square our variables x here, and we want something like x times x, return that. So if I say something like 5 square SQ and 5, it should return us 25, right? Okay, so and a lambda in this, in another hand, would be something like lambda, and x is the variable we're passing into it, and I want for every x value to be times by itself, so same square function. So let's say sqr underscore l, because it's a lambda, and then we want to say something like lsq 5, same sort of thing. So it's just writing a shorthand of a function. That's what lambda means. And so what we're doing each time is we're creating a list of environment functions, functions that hold the environment or return back an environment. So just so you know, yeah, cool. So that wraps our stuff up into an environment. We then want to have some directories to save our stuff to. So these are directories that will either hold our model or hold the logs files for the model once we've created it. And then we want to, I found this class online. It's just a really good callback class function thing to save your model. So yeah, it's pretty simple. So it's a class that references or is inherited from a callback. In the initialization function, we use a super here to call back the original class. We then save those parameters to our global variables in the class, and we then say on step we save the model. And this is just creation of a folder. So yeah, so we got that stuff done. Specify our callback function and where to actually use it. So callback, train the callback function, the frequency at which we're going to save our models. Now these models do get quite large, so you might want to save it every 1,000 steps or every 10,000 steps or something like that. It's worth bearing in mind I ran this particular model for about 100,000 steps, and it was still pretty rubbish. So you might want to run it for 1,000,000 steps and save the check frequency at 10,000 or 100,000. But yeah, it's just in case your program crashes, you've got at least some models saved in your directory. That's the directory we're changing it to. And the part of that really makes a difference is the model. So we're using a PPO model, which is a proximal policy optimization algorithm. Yeah, you can read more about it. Um, I'm not going to talk that much about it. A lot of these functions here originate on the page of stable baselines. So yeah, so you can read a lot of them here. Like it's pretty much you could just pick and pull an algorithm that you like. So out of any of them, you can just pretty much place them into the same place. So you could use, let's say, for example, ASA, the algorithm there, and pretty much just plop it here. You just have to make sure you have the policy correct. So for example, if I was passing images into my machine learning algorithm, I would you want to use a CNN policy. CNN is designed to process images, so that's why you would pass it there. But for now, because of the data I'm actually passing into the object, which I don't think I've spoken about, have I? Yeah, so if I actually look at the state, and because we're actually passing this state into well, we're passing the whole environment into the function, but just to look at what state looks like. Each of these parameters here have a specified value. So I believe the first two is something like the X and Y position of the block, and the other two are the angles of the block. It talks about in the documentation, if I can get that up. So you've got the documentation here, the cart position, the cart's velocity, the pole angle, and the pole angular velocity, and they're specified in the state or observational space, what they call them. Okay, so I know this is kind of getting long-winded now, and I'm kind of talking a lot. But yeah, so you just want to make sure this, because this doesn't have actually any visual data, it's more or less just technical data that's being passed in, you would use an MLP policy. And so we're passing the environment, we're keeping it verbose, so basically we see the output. The log TensorBoard directory here, which we specify there. The learning rate here is about 0, or you can read that, it's lots of zeros. And so we just want to hopefully train this by using model.learn, and we want to specify the number of time steps and the callback function. So we will say something like total time steps is equal to, let's say, 1 million, and we want the callback function to equal callback. So we want to save this every 10,000 steps. Yeah, that'd be fine. Actually, we'll do every 50,000 steps. Sounds better. So yeah, we'll do that, and then now we just run it. So now we just run. So you can see the model here running, and it's doing its stuff. You can see details here. I'm not entirely sure what all these values mean. I looked it up once and I was satisfied with the answer, but right now the exact answer eludes me. So we'll run this, hopefully come back when we have a good concrete model we can work with, or at least when it goes past the 100,000 mark. Okay, so I'm back. The program's finished. We've reached 1 million time steps, which is a rather large number. You can see here total time steps, 1,448. Yeah. Okay, cool. So we got that done. Now all we need to do is actually call this model and make it predict things. So for now, I'm just going to comment this out because we don't want our model to start learning again. We've already done that. Now what I will show you, just one second. So the models have all been saved to my directory here. Okay, yeah. So you can see here, all those zip folders are my models of what the model I saved. And so we're going to call the latest one, which is the 1 millionth model. So, yep. So we're just going to call it first. And what we need to do that is to call the model, we're going to have to load it. So we're going to say, I want you to load the 1 millionth model. Yeah. So model PPO, because that's the model we were using to actually uh, learn it in the first place. Load this particular zip folder. The model will be in our computer's memory, and then we're going to just use this function, well, this snippet of code here. So restart the state so that we start the game from the very beginning. Continuously get the model, predict from the model given the state that we have provided. So the information we provide the model, I want you to predict what the action or the next action will be. So whether that be a 1 or a 0, move left or right. And then we'll pass it into our step function. So we get the environment, which is the game, and we step saying, given the current frame, tell me what to do. That will either be a 1 or a 0. We'll then return this stuff out, so that'll be a reward, whether the game's finished or not, and the state. And then we render the scene. So let's just look at this then. Let's get rid of that if statement. Yeah. Oh, 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 oh. So you can see here the actual object is actually doing quite a bit of work to try and move left and right to try and counteract the pole from falling down. And that actually looks pretty cool. I mean, I left this on for maybe an hour or half an hour, and it's able to do this. It's pretty cool. Obviously, there's certain conditions that if the block moves a certain distance away from the center, the game is considered finished. And so that's why as soon as it moves out of the page, it seems to cut itself off. But still, for if you think about for only this much code, so like essentially one, two, three, was more than three. But yeah, you can see there's not much code for a model that was built just on my own machine to do those sort of tasks. And so the whole beauty of this thing is you can really just draw anything, draw any game using the same framework, plug in this model or plug in these models and play, and just kind of let it do its thing. And you've got a machine learning model already on your machine. That's cool. I mean, you would never expect that. So yeah, I think this covers everything. I'll say thanks for watching, you guys, and I'll catch you next time. If you have any questions as well, let me know in the comments. And if you want to see anything else, let me know too. So I'll catch you next time. Bye bye.